Hello, Steinhauer here. We are beginning our journey in this astronomy class, and we're starting at the beginning with chapter one. Chapter one is a nice introduction to science itself, and particularly the science of astronomy. And it is a brief tour of the universe. And particular importance in this chapter, which we're going to cover pretty much in the first day, is understanding the vastness, the scale of the universe, understanding some of the biggest structures in the universe, understanding some nomenclature before we get started. And it'll be a good chance to practice and get used to some of the concepts and math stuff that we're going to be using throughout the semester. So off we go. Chapter one, Science in the Universe, a brief tour. I'm going to start with one of my favorite quotes about space from Douglas Adams and The Hitchhiker's Guide to the Galaxy that I think, well, let me read it and we can talk about it. Space is big, really big. You just won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down the road to the chemist, but that's just peanuts to space. And this, I think, succinctly and in a humorous way, captures the inadequacies of our brains to even comprehend the sizes of and the numbers that we're going to be encountering this semester. Our brains evolved to be able to experience and handle and understand the immediate surroundings from a survival perspective. They are wholly inadequate to to be able to understand, to be able to fully grok the scale of the universe. So we are left with metaphors, we're left with scale models, we're left with only things we can do is try to bring the vastness of the universe down onto scales that our brains can actually comprehend. So that's one of our goals for this class, at least today. Right, let's start by taking a brief tour of our location in the universe. What is our place in the universe? We have sort of a cosmic address. We're obviously taking this class, at least online, at SUNY Geneseo in the county of Livingston, in the state of New York, in the country of the United States of America, on the planet Earth. And that's sort of where we start in our, so usually where we stop, right? But we can think of our cosmic place in the universe as extending much, much beyond that and even. So of course, we are in a solar system. We are just one planet in a solar system. We think there are 8 other planets, 8 planets total orbiting our sun, and a bunch of and countless other objects, all the way from dwarf planets down to tiny pebbles orbiting the sun. And so we define a star system or a solar system in the case of our sun to be that star and all of the stuff going around it, including its planets and the moons and asteroids and comets and everything else that might be in orbit around that particular star. This is often confused because it has a similar shape with the next thing on our list, which is a galaxy. A galaxy is a star and all of the materials that orbit it. This is often confused. This is often confused with the thing that's coming next, which is a galaxy. A galaxy is similar to a solar system in that they generally have a preferred plane, right? All of the planets in the solar system orbit in the same plane of our solar system. You can draw a single plane and all the planets pretty much lie pretty close to that preferred plane. Galaxies, our galaxy at least anyway, also has a preferred plane. It has a disk. This obviously is not our galaxy. It's impossible to take a picture of our galaxy like this. This is the closest galaxy to us, closest big galaxy to us, the Andromeda Galaxy. But it probably looks similar to what our own Milky Way galaxy looks like. And it too has a disk. The scale, though, is completely different, right? the solar system is a single star, and all of the stuff that surrounds that star. Galaxies are made up of billions, tens of billions, hundreds of billions of stars, all orbiting a common center of mass. So they can be confused because they kind of look the same if you zoom out far enough, but obviously very different scales and very different kinds of objects. Okay, and finally, this is actually probably the most confusing and potentially misleading term on the whole list so far, and that is universe. And when I say universe, I mean the sum total of all matter and energy, everything within and between and all galaxies, everything that exists. And this is slightly different than some other things. One other thing which you'll sometimes refer to this. And I will try to be careful in distinguishing the universe from what I will call the visible universe. Sometimes when people say universe, they really mean visible universe. What I mean by visible universe, basically, it's the same, the sum total of all matter and energy, that same as above, except only that which we can presently observe. I want to see if they can, could potentially, let me erase this, could potentially observe right now. And there are most of the universe actually does not lie within the visible universe. And I'm not even talking about it's too small or it's hidden behind the clouds. I'm talking about light from that part of the universe has not yet reached us, or any kind of information from that part of the universe has not yet reached us. So the visible universe is all the regions of the universe where information could have propagated to us, even if we don't have any information on that right now. Okay, so that's, I will try to be careful in using universe and visible universe, universe, but really this is a concept for the end of the class when we start talking about cosmology. Okay, great. So let's try to think about some scales. How big do you think our Earth is compared to the solar system? So I don't know if you've ever been to Washington, D.C., but if you have not been to Washington, D.C., you should check it out. There's lots of cool stuff to see. And in particular, on the National Mall is a scale, in front of the National Air and Space Museum, is a scale model of the solar system. And this scale model of the solar system, in this scale model, the sun is about the size of a grapefruit. It's about 14 centimeters in diameter. And so the question I have for you is, how big do you think the Earth is on this scale? Do you think it's the size? So let's, let me stop this share and start this share. So here is it's not a grapefruit, it's a ball. It's a little bit bigger than a grapefruit, but you get the basic idea of what the size of the scale model is. And so I want to know, is the Earth, how big is the Earth if we were to put it right next to the sun? Is it the size of a golf ball? That's not a golf ball, but it's about the size of a golf ball. Is it the size of a marble? Is it the size of the ball on the tip of a ballpoint pen? I've got a ballpoint pen here. You can see the ball on the very tip of that ballpoint pen right there. Or is it an atom that's so small that you couldn't possibly see it on the scale? Now, if we were taking this class in person, we would be using Top Hat. I would be asking you what you thought of this particular question. You would be committing to an answer. And honestly, research has showed that it's very important to do this step. We don't have the opportunity to do this live, so I won't be using Top Hat and won't be using any sort of participation in this class in that way. However, every time I ask a question like this in this class, I want you to stop the video and write an answer down. Commit to something. This is important. It helps learning. It breaks misconceptions in ways that I don't even understand fully, but it's really important. So which one do you think it is? It doesn't matter if you're wrong. In fact, being wrong is probably more helpful because it means you're learning something. So it's a zero consequence quiz, but go ahead, pause the video, write something down, and then come back and we'll see what the right answer is. Okay, welcome back. So this, if this is the sun, this is actually way too big. This is actually about the size of Jupiter on this scale, believe it or not. And this is basically the size of the Earth, the ball at the tip of that ballpoint pen. There are about, you could fit about 10 Jupiters across the diameter of the sun, and you could fit about 10 Earths across the diameter of Jupiter. So that is the scale that we're talking about on the Earth. It is the sun, and the Earth is a pretty big place, right? The sun is vastly much larger in comparison. So in this particular case, correct answer would be C, a marble. Okay. Great. So that tells you how large the Earth is compared to the sun. Question I want to ask now is, so here is actually a diagram of the National Air and Space Museum. If you've been there, if you've been there, you know that the Capitol building is in this direction, the Washington Monument's over here, and this is the scale model laid out. So they both have the sizes of these objects and also their relative distance. So if the sun is right here, the Earth is 15 meters away. Okay, so that's a meter is a little bit bigger than a yard, which is 3 feet. So 15 meters is something like 50 feet away, right? If you're familiar with the Newton 202 lecture hall, where we would be having this class if it were in person, that is almost from one end of the front of Newton 202 all the way to the other end of Newton 202. It's a very large distance compared to the sizes of the things we were just talking about. And that's really important. The entire inner part of the planet, of the solar system, is almost entirely empty space. There's a grapefruit in the middle, and 50 feet away is a ballpoint pen sized, tip of a ballpoint pen sized dot that is the Earth. That's the inner part of the solar system. And there's a couple of planets between the sun and the Earth, at least that orbit with smaller orbits than the Earth does. But Venus is also another ballpoint closer to the sun, and the Earth and Mercury is much smaller even than that. Jupiter, Mars, of course, is about 50% further away from the sun than the Earth is. You get to Jupiter out here at 78 meters. You get to Saturn out here at 143 meters, and Uranus at 287. Neptune is all the way past the Hirshhorn Museum, if you're familiar with the National Mall, out here at almost a half a kilometer away from the sun. So that is the inner part of the solar system. The solar system itself is almost entirely empty space. And the solar system is one of the more crowded places in the galaxy, which is way more crowded than the universe itself. Space is vast in a way that our brains, as I said before, can't really comprehend. Okay, there is a cool animation that I'll put a link to in this week's on the page that you should check out that sort of, I think, drives this home as well. So be sure to check that out. Okay, so here's another question for you. On this same scale, where the sun is a grapefruit-sized thing in Washington, D.C. On the mall, the question is, how far would you have to walk to reach Alpha Centauri. Alpha Centauri is famous because it is the closest star to the Earth other than the sun. So again, it's about a half a kilometer out to Neptune. That sort of defines the planetary part of the solar system. How far do you have to walk to get to the next closest star? Is it a mile? Is it 10 miles? Is it 100 miles? Is it 2,500 miles? What do you think? How far you'd have to walk on the same scale to get to the next closest star? I'll let you pause the video, write down a guess, and I'll come back and we'll talk about the answer. Okay, welcome back. So what do you think? It turns out that the answer is the distance across the US, 2,500 miles. It is, as I said, the inner part of the solar system itself is a very crowded region of the galaxy. Most of the galaxy, there are no stars. The next closest star to the sun is a second grapefruit in San Francisco, if the first grapefruit of the sun is in Washington, D.C. And if you were to do the whole galaxy on this, I've got a cool flash animation here that doesn't work anymore, but you can zoom out on this scale where the sun is a grapefruit and the next closest sun is in San Francisco. The galaxy takes up most of the inner part of the solar system. So again, we're starting to conflate our model with reality, but that's what you get. It's just enormous. It's a 10 billion to 1 scale. Okay, great. So how big is the universe? Now it gets even crazier. The Milky Way is one of about 100 billion galaxies. Oh, those 10 to the 11 did not show up very well. Apologies. This should be 10 to the 11, and this should be 10 raised to the 11th power. If there are 100 billion, there are 100 billion stars in our galaxy. That's 10 to the 11. 10 to the 11 is an extraordinarily large number. It's a 1 with 11 zeros after it. I'm just going to write this number down here real quick. Watch this. This is 100. This is 100 billion. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's throw some commas in here so we can see what's going on. That's 100 billion. It's a 1 with 11 zeros after it. Again, that's a number that my feeble brain cannot possibly wrap itself around. I can't even really fathom a million. 100 billion is beyond me. Now, and that's just how many stars there are in our galaxy. Turns out there are 100 billion galaxies in the visible universe. Let me make sure I put that in there. There are 100 billion galaxies in the visible universe, just the part of the universe that we can presently have potential to see. And so, if you take 110 to the, this is if you take 10 to the 11 stars in our galaxy and multiply that by 10 to the 11 galaxies in the visible universe, you will get a number that is even much larger than this. And this is where it helps to use scientific notation. It helps to write your big numbers like this instead of like this. Because if I were to ask you on a piece of paper to multiply these two numbers, you would have a hard time doing that. You'd be counting, it'd be easy to mess things up. These two numbers over here are much easier to multiply together because there's a secret to it, is a trick. If you don't know it, it's pretty simple. These two numbers are essentially, let me write them a little bit differently. Each of these numbers have a base and an exponent. I haven't written the base because the base is just 1, but I could rewrite these numbers as 1 times 10 to the 11 times 1 times 10 to the 11. And when you're multiplying two numbers in scientific notation, you multiply the bases and you add the exponents. So 1 times 1 is just 1. And 11 plus 11 is 22. So 10 to the 11 times 10 to the 11 is 1 times 10 to the 22, and I can ignore the 1 because it's just there, is actually just 10 to the 22. And that's an even crazy bigger number. A 1 with 22 zeros after it. Let me just write that down because it's a ridiculous number. 1, so 22 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Put some commas in there. 1, 2, 3, 4, 5, 6, 7. That's a number whose name I don't even know. It's a number that is, as they say here, how can you fathom that number? It is as many stars as there are grains of sand on all of Earth's beaches combined. Those are the kinds of numbers we're going to be talking about in this class. Okay, one more scale thing, and then we'll get to some other concepts. So that's the extent of the universe. Those are some of the numbers we're talking about in terms of how big it is and how much stuff is in it. But it's also useful to think about the time of the universe. It turns out, we know the age of the universe. It's about 14 billion, 13.8 billion years old. We'll get to how we know that number and where it comes from later on in the class. But again, 14 billion years is a number that's too big to comprehend. So Carl Sagan was the first person or one of the first people to make this analogy. Let's compress the entire 14 billion year history of the universe down into a single year. And if we do that, what do things look like? When do things happen? A year is a long period of time in our daily lives, but it's a unit of measure and time that we can comprehend. We can wrap our brains around what a year is. So what does that look like? Well, here is the cosmic calendar, right? On this scale, each month represents more than 1 billion years. A day represents about 40 million years. Each second in this clock represents about 440 years. So let's think about this. The universe begins on January 1st, obviously, and February, March, and April are interesting times for galaxy formation and early processings of the very earliest stars in the universe. What we would call the Milky Way as some sort of collection of stars with some spiral shape probably doesn't even take shape until May of our cosmic calendar. It's several billion years before we think an entity that we would recognize as a spiral galaxy known as the Milky Way would come into being. Our solar system, the sun, doesn't even form until September. The Earth is only the sun is only about 4.5 billion years old, and that is far less than the age of the universe. So the sun, the Milky Way, forms in May. The sun doesn't even form until September. We think once the sun forms, the planets are basically formed at the same time. And so again, October, Earth's atmosphere is just getting oxygen. Very first complex life forms might start appearing in November, right? And then when we get down to it, vertebrates appear on December 19th. Land plants don't appear until December 20th. The dinosaurs don't even come onto the Earth until Christmas Day, December 25th. Things that we would call mammals don't occur until the next day. Dinosaurs don't go extinct until December 30th. Yesterday, on our cosmic calendar, the dinosaurs went extinct. And obviously, humans don't even come into being. All of human history is in the last 30 seconds. Let's zoom in a little bit and see if we can see how December 31st is going to look. Things that we would call humanoids, early hominids don't arrive until 9 p.m. Things that we would actually call Homo sapiens don't come until 11:58 p.m. 25 seconds ago, agriculture's arriving. 1 second ago, we were showing that the Earth orbits the sun and proving that, what our place in the universe actually was. So all of recorded history, our lives are, 0.05 seconds old at this point on this cosmic calendar. So just to put some stuff into perspective, give you a sense of where we are, and hopefully give you a model to wrap your brain around. Okay, I'll stop there for now. I'll come back with more stuff in the next video. See you then.